Hello, welcome to this video. Today we're going to be talking about energy transfers in three different scenarios. The first of these scenarios is a ball being projected upwards. So this is a diagram we're going to be using. We're going to be imagining a person throwing the ball up and it follows this trajectory, and we're going to be considering the different energies at the different points of E1, E2, E3 and E4. So initially at E1 we can see the ball is going to be projected upwards with a speed of v. But the initial energy just before this, the only one it really has is going to be the potential energy it has by virtue of its position. So as we can see, it's h meters off the ground, so therefore the initial energy is going to be mgh. And then the energy due to the projection of it, so it's being projected with a speed of v, obviously has a mass, we're going to consider that m. The kinetic energy that's going to have then is half mv squared. So the initial energy, the total initial energy, should I say, is the summation of gravitational potential energy and kinetic energy. So it's mgh add half mv squared. So the ball is going to travel all the way up to the position of at the top of the trajectory, and at this point it's lost all its speed, and it's going to start gaining speed after this. But at this point it's got absolutely no speed, so v equals 0. Obviously, because of that, the kinetic energy is 0, but we can see that all the energy it had has become potential energy. So it's not energy it possesses, it's energy that it could have. So at this point we can see that the height is 3h meters, which means that the gravitational potential energy is 3 mgh, and that's the total energy. As the ball travels to E3, this is essentially returned to its initial conditions. It has the same gravitational potential energy, and the gravitational potential energy that it gained has become kinetic energy. So as we can see, the kinetic energy is half mv squared. We can also equate this to 2 mgh, as it is from the gravitational potential energy, it's lost 2 mgh joules of gravitational potential energy that has become kinetic energy, and the gravitational potential energy it still has is equal to mgh. Now if it continues its trajectory from here to the ground, the instant before the impact with the ground, the ball will have only kinetic energy. It's going to have h equals 0, so therefore the gravitational potential is going to be 0. So the whole 3 mgh joules of gravitational potential had at E2 has become kinetic energy, therefore half mv squared equals 3 mgh. And you could work out the speed it was at by rearranging that equation, and if you knew h and the initial speed, then you'd be able to calculate that. After the impact, the ball's going to either bounce or break if it's a glass ball or something like that, and it's going to lose its energy through heat to the rest of the environment. It's going to lose that to stones on the ground or just the rest of the environment. The second scenario we're going to be looking at is boiling a kettle. Might seem very simple, but it's a good way to think about different energy transfers. So the initial energy is going to be supplied by either an electrical supply or an open fire. Obviously you plug your kettle in at home, the electricity comes through and heats up the element in the kettle, and it's going to heat your water. But sometimes people obviously boil water on open fires or gas fires and things like that. So the thermal energy supplied by the supply, whether that's obviously the electrical supply or the open fire, increases the kinetic energy of the water molecules, and hence this raises the water's temperature. So this can be considered thermal energy or the kinetic energy of the water molecules. Now some of the energy supplied whilst heating will be wasted, as it is going to heat the environment, especially if it's an open fire. It's going to heat the air, and then it's also going to heat the outside of the kettle, and that's going to be wasted also to the environment. And also after the water is boiled, it's going to be constantly losing energy to the surroundings, through, again, just heating the environment. The final scenario we're going to be looking at is a vehicle slowing down. Now this is one that's not completely intuitive. You've got maybe know something a little bit about cars or something like that, but it's always good to know. So a car travelling at the speed of v meters per second is going to have an initial energy, it's all going to be kinetic energy, of half mv squared. And when the brakes are applied, there's a frictional force between the brakes and the tyres. the brake is going to sort of clamp onto the tyre or tap it or something like that, and this means that the brakes are going to heat up, and therefore the kinetic energy of the car, and therefore the speed, is going to be reduced. Additionally, there's always friction between the tyres and the road. That happens just driving anyway. It's not just when you're braking, and that's why the tyres of a car will become hot. Specifically, especially after a long car journey. Obviously, it happens all the time, but it's much more noticeable after you have a very long drive. But this is also where some of the kinetic energy of the car also dissipates during braking or driving.